What if everything we think we know about the universe is just the tip of the iceberg? Beneath the surface of our visible reality lies a hidden world, dimensions beyond our perception, that could hold the answers to the greatest mysteries of existence. Black holes, dark matter, the very fabric of space and time. What if these phenomena are merely glimpses of a deeper, more complex reality? Today, we're venturing into the extraordinary realm of 36 hidden dimensions theories, ideas that stretch the boundaries of human understanding and challenge the very foundations of physics. From the intricate webs of string theory to the mind-bending concepts of Brane worlds, these theories aren't just abstract musings. They could be the keys to unlocking secrets that have eluded us for centuries. If you've ever wondered what lies beyond the edges of our known universe or how the cosmos operates on a level we can't see, this journey is for you. Let's dive in and explore how these hidden dimensions might just rewrite the story of everything we thought we knew. Picture this, our universe as a flat sheet of paper, smooth and two-dimensional, while hidden dimensions are like intricate folds or layers tucked away, invisible to our eyes. This simple analogy helps us grasp the mind-bending idea that there might be more to reality than the three spatial dimensions we're familiar with: length, width, and height. But what if there are more? What if, beyond what we can see and touch, there are additional dimensions curled up or compactified so tightly that they evade our detection? This isn't just science fiction, it's a concept that has fascinated physicists for over a century. It all started with the Kaluza-Klein Theory in the early 1900s, which proposed that a fifth dimension could unify gravity and electromagnetism. While this idea didn't fully hold up, it planted the seeds for something far more profound: string theory. In the modern era, string theory suggests that the fundamental particles of the universe aren't just tiny dots but vibrating strings, and these strings might dance across as many as 10 or even 11 dimensions. But why would we need these extra dimensions? One compelling reason lies in the strange behavior of gravity. Compared to the other fundamental forces, like electromagnetism or the strong nuclear force, gravity is astonishingly weak. Why is it so feeble? Some physicists believe the answer lies in hidden dimensions. Gravity, they argue, might be leaking into these unseen layers, spreading its influence across multiple dimensions and diluting its strength in our observable universe. This could explain why gravity feels so much weaker than the other forces. It's not weak at all. It's just operating on a scale we can't fully perceive. These hidden dimensions aren't just theoretical curiosities. They could be the key to solving some of the most profound mysteries of the cosmos. From the nature of dark matter to the bizarre behavior of black holes, these unseen layers might hold the answers we've been searching for. And as we peel back the layers of reality, we might just find that the universe is far more complex and far more beautiful than we ever imagined. Now, let's take a closer look at one of the most fascinating frameworks in modern physics: string theory. This groundbreaking idea doesn't just tweak our understanding of the universe, it completely transforms it. Instead of thinking of particles as tiny, solid dots, string theory proposes that everything, from the quarks inside atoms to the photons zipping through space, is made up of incredibly small, vibrating strings. These strings aren't just random vibrations, they're the cosmic symphony, each note corresponding to a different particle or force in the universe. But here's where it gets truly mind-bending. For this theory to work mathematically, our universe can't just have the three spatial dimensions we know. It needs 10. Why 10? Well, the math simply falls apart without them. 6 of these dimensions aren't missing, they're just hidden, curled up so tightly that they're impossible for us to detect with our current tools. To visualize this, think of a garden hose. From far away, it looks like a simple line, a one-dimensional object. but if you zoom in, you'll notice the hose has a circular shape, a second dimension wrapped around its length. The hidden dimensions in string theory are like that circular dimension, tiny, compact, and all around us, yet invisible from our macroscopic perspective. This isn't just a clever trick to make the math work. These extra dimensions might hold the key to one of physics' greatest challenges, unifying the fundamental forces of nature. Gravity, electromagnetism, and the nuclear forces all seem to operate by different rules, but string theory suggests they're simply different vibrations of the same cosmic strings, playing out across these 10 dimensions. It's as if we've been listening to a single instrument in an orchestra, unaware of the full symphony happening all around us. What's truly remarkable is how string theory bridges the gap between the very small and the very large. It connects the quantum world of particles to the vast cosmic dance of galaxies and black holes. And while we can't yet prove its existence experimentally, the elegance of its mathematics and its potential to explain the universe's deepest mysteries make it one of the most compelling ideas in science. So, as we explore these hidden dimensions, we're not just uncovering new layers of reality. We're stepping into a universe far richer and more intricate than we ever imagined. But what exactly are these hidden dimensions made of? Enter Calabi-Yau manifolds, the enigmatic geometric shapes that string theory proposes as the framework for these unseen layers of reality. Imagine a shape so complex, so intricate, that it exists in 6 dimensions, yet is folded and twisted in ways that make it almost impossible to visualize. These manifolds aren't just mathematical curiosities. They're the stage upon which the cosmic strings of string theory vibrate, producing the particles and forces that make up our universe. To get a sense of what a Calabi-Yau manifold looks like, picture a snowflake, but instead of 6 symmetrical arms, it's a swirling, multidimensional tapestry of curves and folds, each twist and turn influencing the behavior of the strings that reside within it. These shapes aren't random. Their geometry determines the properties of particles and forces. For example, the way a string vibrates around a Calabi-Yau manifold could determine whether it becomes an electron, a photon, or even a quark. In this way, these manifolds aren't just passive structures, they're active participants in shaping the very fabric of reality. What makes Calabi-Yau manifolds so fascinating is their potential to explain some of the universe's most perplexing phenomena. Take dark matter, for instance. This mysterious substance makes up about 85% of the matter in the cosmos, yet it doesn't interact with light or ordinary matter in any way we can detect. Could the properties of Calabi-Yau manifolds hold the key to understanding dark matter? Some physicists think so. They suggest that particles associated with these hidden dimensions might be the elusive dark matter we've been searching for, existing just out of reach in the folds of these complex shapes. And it's not just dark matter. The behavior of particles in our observable universe, their masses, charges, and interactions, could all be influenced by the geometry of these manifolds. If we could map out the structure of a Calabi-Yau manifold, we might unlock the secrets of why the universe looks and behaves the way it does. It's like discovering the blueprint of reality hidden in plain sight. Yet, as intriguing as this idea is, it's also incredibly challenging. Calabi-Yau manifolds are so complex that even the most advanced mathematical tools struggle to fully describe them. And because they exist in dimensions beyond our perception, we can't directly observe or measure them yet, but that hasn't stopped physicists from exploring their possibilities. By studying these shapes mathematically, we're inching closer to understanding how they might shape the universe on both the smallest and largest scales. So, while Calabi-Yau manifolds might seem like abstract mathematical constructs, they could hold the answers to some of the most profound questions in physics. From the nature of particles to the mysteries of dark matter, These intricate shapes are more than just theoretical, they're a window into a deeper, hidden reality waiting to be uncovered. What if our universe isn't the full picture, but just a tiny slice of something much larger? Imagine our reality as a three-dimensional sheet, floating like a leaf in a vast, higher-dimensional ocean. This is the core idea behind Brane worlds, a theory that suggests our universe might exist on a membrane or brane, embedded within a space that has more dimensions than we can perceive. It's a concept that sounds like science fiction, but it could hold the key to explaining some of the most baffling mysteries of physics. In the Brane world scenario, our universe isn't isolated. It's part of a larger, multidimensional landscape where other branes might exist, each potentially hosting their own universes with their own laws of physics. This idea isn't just fascinating, it's also practical. For instance, it could explain why gravity feels so weak compared to the other forces. If gravity isn't confined to our brane but can leak into these extra dimensions, its strength would be diluted, making it appear feeble in our three-dimensional world. It's like trying to hear a whisper in a crowded room. The sound is there, but it's being drowned out by the noise of the larger space. But Brane worlds aren't the only radical idea reshaping our understanding of reality. Enter the holographic principle, a concept so profound it challenges how we think about space, time, and information itself. This principle suggests that all the information contained within a volume of space, everything from the stars in a galaxy to the particles in a grain of sand, can be encoded on its two-dimensional boundary like a hologram. In other words, our three-dimensional universe might just be a projection of information stored on a two-dimensional surface. It's as if the universe is a cosmic movie, and the screen it's projected on is infinitely thinner than we ever imagined. The holographic principle doesn't just stretch our imagination, it also has practical implications. It could help resolve one of the biggest puzzles in modern physics, the black hole information paradox. If information can't be destroyed, as quantum mechanics suggests, then what happens to all the information that falls into a black hole? The holographic principle offers a solution. The information isn't lost, it's encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This idea bridges the gap between quantum mechanics and general relativity, two theories that have long resisted unification. Together, Brane worlds and the holographic principle paint a picture of a universe far stranger and more interconnected than we ever imagined. They challenge our most basic assumptions about space and time, suggesting that what we see and experience might just be the surface of a much deeper reality. And as we continue to explore these ideas, we're not just uncovering new layers of the cosmos, we're redefining what it means to exist within it. What if our universe is just one bubble floating in an infinite cosmic foam? This is the mind-bending idea behind the multiverse, a concept that suggests our reality is just one of countless universes, each with its own unique laws of physics. But how does this connect to hidden dimensions? If we think of each universe as a bubble, the spaces between them, those hidden dimensions could act as bridges linking these worlds in ways we're only beginning to imagine. Imagine blowing soap bubbles. Each bubble is its own little world, floating independently, yet they're all part of the same foam. In the multiverse, these bubbles represent universes separated by the boundaries of space and time. But here's the twist: hidden dimensions might allow these bubbles to interact, even if only faintly. These interactions could explain some of the strangest phenomena in our universe, like why the cosmos appears so uniform on the largest scales. Take the cosmic microwave background, for example, the faint glow left over from the Big Bang. This radiation is almost perfectly uniform, which is puzzling because in the standard model, distant regions of the universe shouldn't have had enough time to reach the same temperature. But if our universe is part of a multiverse, hidden dimensions could have allowed energy or information to flow between bubbles, creating a kind of cosmic equilibrium. It's like heat spreading through a network of pipes connecting distant rooms in a vast, unseen structure. This idea doesn't just solve puzzles, it also opens up thrilling possibilities. If hidden dimensions act as bridges between universes, could we ever detect their influence? Some scientists speculate that subtle ripples in space-time or anomalies in the distribution of galaxies might be traces of these interactions. While we don't yet have the tools to confirm this, the mere possibility is enough to spark the imagination. The multiverse theory, combined with hidden dimensions, challenges us to rethink the very nature of reality. It suggests that our universe isn't an isolated island but part of a vast, interconnected web of worlds. And as we explore these ideas, we're not just uncovering new layers of the cosmos, we're redefining what it means to exist within it. The multiverse might be the key to understanding not just our place in the universe, but our place in a reality far grander and more mysterious than we ever dreamed. One of the most perplexing puzzles in modern physics is the hierarchy problem, a question that cuts to the very heart of why the universe works the way it does. Why is gravity, the force that holds galaxies together and shapes the cosmos, so incredibly weak compared to the other fundamental forces? To put it in perspective, the electromagnetic force is about 1 trillion times stronger than gravity. That's like comparing the strength of a hurricane to the faintest breath of wind. This imbalance doesn't just confuse scientists, it challenges our understanding of how the universe is built. Hidden dimensions might hold the key to solving this mystery. If gravity isn't confined to our three-dimensional world but instead spreads out across higher dimensions, its strength could be diluted, making it appear weak in our observable universe. Think of it like this: if you spill water on a flat table, it spreads out and becomes thin, but if you pour it into a deep bucket, it stays concentrated. Gravity, in this scenario, is like the water on the table spread thin across dimensions we can't see, which is why it feels so much weaker than the forces confined to our three-dimensional space. This idea isn't just theoretical, it's being put to the test. At the Large Hadron Collider, physicists are smashing particles together at nearly the speed of light, searching for clues that might reveal these hidden dimensions. If extra dimensions exist, they could leave subtle fingerprints in the debris of these collisions, such as missing energy or unexpected particle behavior. While we haven't found definitive proof yet, the possibility is tantalizing. Discovering even a hint of these dimensions wouldn't just solve the hierarchy problem, it would revolutionize our understanding of physics itself. Imagine what it would mean if we could confirm the existence of these hidden dimensions. It wouldn't just explain why gravity is so weak, it would open the door to a deeper understanding of the universe's fundamental structure. From the behavior of black holes to the nature of dark energy, these extra dimensions could provide the missing pieces to some of the most profound puzzles in science. And as we continue to explore, we're not just uncovering new layers of reality, we're redefining what it means to understand the cosmos. The search for hidden dimensions isn't just a scientific endeavor, it's a journey into the very fabric of existence. Long before string theory or Brane worlds entered the scene, the idea of hidden dimensions was already sparking curiosity in the minds of physicists. In the early 1900s, two names stand out as pioneers in this bold exploration: Theodore Kaluza and Oskar Klein. Their groundbreaking work, now known as the Kaluza-Klein Theory, was the first serious attempt to weave together the forces of nature using the concept of extra dimensions. Kaluza, a mathematician with a flair for bold ideas, proposed something extraordinary in 1919. He suggested that if we added a fifth dimension to Einstein's theory of general relativity, It could unify gravity, the force that governs the cosmos, with electromagnetism, the force that powers our lights and electronics. At first glance, the idea seemed almost too elegant to be true. By introducing this extra dimension, Kaluza showed that the equations describing gravity and electromagnetism could emerge from a single, unified framework. It was as if he had found a hidden thread connecting two seemingly unrelated forces, pulling them together into a coherent whole. But what exactly was this fifth dimension? Oscar Klein, building on Kaluza's work, proposed that it wasn't some vast, visible expanse like the three dimensions we know. Instead, it was curled up, compactified into an incredibly tiny scale, so small that it would be impossible for us to detect with our current technology. To visualize this, think of a garden hose. From a distance, it looks like a simple line, but up close, you can see it has a circular shape, a second dimension wrapped around its length. Klein's fifth dimension was like that circular shape, hidden, compact, and all around us, yet invisible to our everyday perception. At the time, this idea was revolutionary. For centuries, physicists had worked within the framework of three spatial dimensions, and suddenly, here was a theory suggesting there might be more. While the Kaluza-Klein theory didn't fully hold up under closer scrutiny, it couldn't account for all the forces or particles we know today. It planted a seed that would grow into something extraordinary. It showed that extra dimensions weren't just a mathematical curiosity. They could be a powerful tool for understanding the universe. This bold step paved the way for later theories like string theory and Brane worlds, which took the concept of hidden dimensions and ran with it. Kaluza and Klein's work reminded physicists that sometimes the answers to our biggest questions lie in places we haven't yet thought to look. Their fifth dimension was the spark that ignited a century of exploration into the hidden layers of reality, inspiring generations of scientists to dream bigger and dig deeper. Today, as we grapple with the mysteries of dark matter, black holes, and the fundamental forces, we owe a debt to these early visionaries. Their theory may not have been the final answer, but it was the first step on a journey that continues to reshape our understanding of the universe. And as we move forward, we carry their legacy with us, always asking, what else might be hidden just out of sight, waiting to be discovered? So, how do these hidden dimensions stay hidden from us? The answer lies in a process called compactification, a way of imagining how extra dimensions could be curled up or folded so tightly that they're invisible to our everyday perception. Picture a carpet rolled up tightly. From a distance, it looks like a simple cylinder, but if you were to unroll it, you'd see its full, intricate surface. The extra dimensions in our universe might be like that rolled-up carpet present, but so compact that they're undetectable at the macroscopic scale we experience. This idea of compactification isn't just a clever metaphor. It's a crucial piece of the puzzle in theories like string theory and Brane worlds. If extra dimensions are too small to see, how do they affect the world around us? The answer lies in their size and shape. Just as the way a carpet is rolled tightly or loosely, at an angle or straight, can change its appearance, the way extra dimensions are compactified could influence the fundamental laws of physics in our observable universe. For example, the vibrations of cosmic strings in string theory depend heavily on the geometry of these hidden dimensions. A slight change in their shape could mean the difference between an electron and a quark, or even determine the strength of gravity itself. But why would these dimensions need to be so small? Think of it this way. If extra dimensions were large and expansive, we'd likely have noticed their effects by now. Gravity, for instance, would behave very differently, spreading out into these extra spaces and weakening far more dramatically than it does in our three-dimensional world. The fact that gravity follows the inverse square law, meaning it weakens with the square of the distance, suggests that any extra dimensions must be incredibly tiny. on a scale far smaller than an atom. It's like whispering in a vast hall. The sound dissipates quickly, but in a small room, it stays concentrated and strong. This concept of compactification isn't just theoretical, it's a practical necessity for making sense of the universe. Without it, the math behind string theory and Brane worlds wouldn't hold together. These theories rely on the idea that extra dimensions are curled up in specific ways, creating the precise conditions needed for particles and forces to behave as they do. In a sense, the geometry of these hidden layers is the unseen architect of reality, shaping everything from the smallest particles to the largest structures in the cosmos. And here's where it gets even more fascinating. The shape of these compactified dimensions isn't arbitrary. It's thought to be determined by Calabi-Yau manifolds, those intricate, multidimensional shapes we discussed earlier. These manifolds aren't just mathematical curiosities. They're the framework that dictates how strings vibrate and interact, ultimately defining the properties of the particles and forces we observe. It's as if the universe has a hidden blueprint written in the language of geometry that we're only beginning to decode. As we explore the idea of compactification, we're not just uncovering a clever way to hide extra dimensions, we're peeling back the layers of a universe far more intricate and interconnected than we ever imagined. From the tiniest vibrations of strings to the vast expanse of the cosmos, these hidden dimensions remind us that reality is far stranger and far more beautiful than it appears. While we've explored how hidden dimensions might reshape our understanding of gravity and the fundamental forces, there's another cosmic mystery they could help unravel, one that's been baffling scientists for decades: dark matter. This invisible substance makes up about 85% of the matter in the universe, yet it doesn't interact with light or ordinary matter in any way we can detect. It's like a ghostly presence felt only through its gravitational pull on galaxies and galaxy clusters. But what if dark matter isn't just hiding in plain sight? What if it's lurking in the hidden dimensions we've been discussing? Imagine standing in a room with a single light source and an object casting a shadow on the wall. You can't see the object directly, but its shadow gives you clues about its shape and size. Dark matter might be something like that shadow, a glimpse of something existing in a higher dimensional space, leaving faint traces in our three-dimensional world. In this scenario, dark matter particles could reside in these extra dimensions, interacting with our universe only through gravity, the one force that can traverse between dimensions. This would explain why dark matter is so elusive. It's not just invisible, it's operating in a space we can't access. This idea isn't just speculative, it's grounded in some of the most cutting-edge theories in physics. One such theory suggests that dark matter particles could be massive but confined to these extra dimensions, making them nearly impossible to detect through conventional means. Their gravitational influence, however, would still seep into our world, tugging on galaxies and bending the fabric of space-time. It's like feeling the vibrations of a drum through a wall. You can't see the drum, but you know it's there because of its effects. If this theory holds, it could solve one of the biggest puzzles in cosmology: why dark matter seems to dominate the universe's mass yet remains so utterly invisible. By connecting dark matter to hidden dimensions, we might finally have a framework to explain its existence and behavior. It's a tantalizing possibility that bridges the gap between the visible and the unseen, offering a new way to think about the cosmos. But how do we test such an idea? One approach involves looking for subtle anomalies in the way gravity behaves on cosmic scales. If dark matter particles are indeed leaking gravitational influence from higher dimensions, we might detect tiny deviations in the way galaxies rotate or how light bends around massive objects. These clues, though faint, could be the key to unlocking the secrets of dark matter, and by extension, the hidden dimensions themselves. As we continue to explore this connection, we're not just solving a scientific mystery, we're redefining our understanding of the universe's very fabric. The idea that dark matter might exist in dimensions beyond our perception challenges us to think bigger, to look deeper, and to imagine a reality far more complex and far more interconnected than we ever realized. And in doing so, we might just uncover the missing piece of the cosmic puzzle that has eluded us for so long. Gravity, the force that holds planets in orbit and shapes the cosmos, might not be what it seems in the grand scheme of the universe. In our familiar three-dimensional world, gravity feels like the weakest of the fundamental forces, barely noticeable compared to the electromagnetic forces that power our devices or the strong nuclear forces binding atoms together. But what if gravity's apparent weakness is just an illusion? What if, in higher dimensions, it's actually far stronger, its power diluted only because it's spreading out across realms we can't see? To understand this, let's step into the world of higher dimensions. Imagine gravity as a kind of energy, like light radiating from a bulb. In our three-dimensional space, that light spreads out in all directions, weakening as it travels further from the source. But if there were extra dimensions, gravity wouldn't just spread out in three directions. It would spill into those unseen layers, thinning out its strength in our observable universe. It's like pouring water into a sponge. Some of it stays on the surface, but much of it soaks into the hidden spaces below. This could explain why gravity feels so feeble to us. It's not weak, it's just leaking into dimensions we can't access. Interestingly, the strength of gravity in higher dimensions isn't fixed. It depends on how many extra dimensions exist and how they're shaped. In some theories, like brain-world scenarios, gravity could be much stronger in higher dimensions, confined only partially to our three-dimensional brain. This would mean that what we perceive as gravity's weakness is actually a clue to the existence of these hidden layers. It's as if we've been observing only a fraction of gravity's true power, with the rest hidden in plain sight. But how do we test such a radical idea? Enter the world of high-energy physics experiments. At facilities like the Large Hadron Collider, scientists are smashing particles together at incredible speeds, searching for signs of extra dimensions. If gravity is stronger in higher dimensions, these collisions might produce tiny, fleeting effects, like missing energy or unusual particle behavior that could hint at gravity's hidden nature. While no definitive proof has been found yet, even the possibility is enough to spark excitement. Discovering evidence of higher dimensions wouldn't just solve the puzzle of gravity's weakness. It would open a window into a universe far more complex than we ever imagined. This exploration of gravity in higher dimensions isn't just about solving a scientific mystery, it's about redefining our understanding of the cosmos. It challenges us to think beyond the limits of our three-dimensional experience and consider a reality where the forces we take for granted might behave in ways we can barely comprehend. As we continue to probe the nature of gravity, we're not just uncovering new layers of the universe, we're stepping into a hidden world waiting to be discovered. What if the hidden dimensions we've been exploring aren't just tiny, curled-up spaces but vast, expansive realms stretching far beyond our perception? This is the bold claim of the large extra-dimension hypothesis, a theory that flips the script on how we imagine these unseen layers of reality. Instead of thinking of extra dimensions as microscopic folds, this idea suggests they could be enormous, large enough to fundamentally alter our understanding of gravity and the very fabric of space itself. To visualize this, picture our universe as a sheet of paper floating on the surface of an immense, unseen ocean. The paper represents the familiar three dimensions we experience every day, while the ocean beneath it symbolizes these large extra dimensions. Just as water can seep into the paper, gravity might be leaking into these vast, hidden layers, spreading its influence far beyond our observable universe. This could explain why gravity feels so weak in our world. Its strength isn't diluted by tiny, compact dimensions, but by an expansive, higher-dimensional space that absorbs its power. The implications of this idea are staggering. If these extra dimensions are large, they wouldn't just affect gravity, they could fundamentally reshape how we think about the universe. For example, particles or forces we thought were confined to our three-dimensional world might actually exist in these higher dimensions, interacting with our reality in ways we're only beginning to understand. It's like discovering that the world you've been living in is just a tiny island in a vast, uncharted sea, one that holds secrets waiting to be uncovered. This hypothesis also challenges our understanding of space itself. We often think of space as a fixed, unchanging stage where the drama of the universe unfolds. But if large extra dimensions exist, space might be far more dynamic and interconnected than we ever imagined. It's as if the stage we've been standing on is just one layer of a much larger theater, with hidden rooms and corridors influencing the play in ways we can't see. What's truly exciting is how this idea ties into experiments like those at the Large Hadron Collider. If these large extra dimensions are real, they might leave subtle clues in the debris of high-energy particle collisions. For instance, missing energy or unexpected particle behavior could hint at gravity's escape into these unseen realms. While we haven't found definitive proof yet, the possibility is tantalizing. Discovering even a hint of these dimensions wouldn't just solve the mystery of gravity's weakness, it would revolutionize our understanding of the cosmos. As we explore the large extra dimension hypothesis, we're not just challenging our assumptions about space and gravity, we're opening the door to a universe far more expansive and interconnected than we ever dreamed. It's a reminder that reality, as we know it, might just be the tip of an unimaginably vast iceberg with hidden depths waiting to be explored. And as we journey deeper into these ideas, we're not just uncovering new layers of the cosmos, we're redefining what it means to exist within it. Black holes have long been one of the most enigmatic objects in the universe, cosmic vacuums so powerful that not even light can escape their grasp. But what if these mysterious entities aren't just regions of extreme gravity? What if they're gateways to something far stranger, other dimensions, or even other universes? This is where hidden dimensions come into play, offering a radical new perspective on black holes and the role they might play in the grand tapestry of reality. One of the most intriguing ideas is that black holes could act as portals to higher dimensions. Imagine a black hole not as a dead end, but as a cosmic tunnel, its intense gravitational field warping spacetime so dramatically that it creates a bridge to another realm. In this scenario, the singularity at the center of a black hole, the point where gravity becomes infinite, might not be a destructive endpoint but a doorway. Matter and energy falling into a black hole wouldn't be lost forever. Instead, they could be funneled into these hidden dimensions, emerging in another universe or a distant part of our own. It's a concept that sounds like science fiction, but it's grounded in some of the most cutting-edge theories in physics. This idea could also help solve one of the biggest puzzles in modern science, the black hole information paradox. According to quantum mechanics, information can never be destroyed. Yet, when matter falls into a black hole, it seems to vanish completely, leaving no trace behind. How can these two ideas coexist? Hidden dimensions might hold the answer. If the information isn't lost but instead transferred to another dimension or universe, the paradox could be resolved. It's as if the black hole isn't a destroyer but a transporter, sending data, and perhaps even entire worlds, to places we can't yet see. But how does this change our understanding of black holes? For starters, it transforms them from cosmic vacuum cleaners into dynamic, multidimensional structures. Instead of being regions of pure destruction, They could be vital components of a larger cosmic network, connecting different parts of the universe or even different universes in ways we're only beginning to imagine. This idea also ties into the holographic principle, which suggests that all the information within a black hole might be encoded on its surface, its event horizon. Hidden dimensions could provide the framework for how this encoding works, acting as the bridge between the two-dimensional surface and the three-dimensional interior. What's truly fascinating is how this shifts our perspective on black holes. They're no longer just gravitational anomalies, they're potential keys to understanding the universe's deepest secrets. From resolving paradoxes to revealing the existence of hidden dimensions, these enigmatic objects might hold the answers to questions we haven't even thought to ask. And as we continue to explore these ideas, we're not just redefining black holes, we're reimagining the very nature of reality itself. The next time you gaze at the night sky, remember, those dark, mysterious voids might just be the most important pieces of the cosmic puzzle. What if everything we see, touch, and experience is nothing more than a cosmic illusion, a projection of information encoded on a two-dimensional surface? This is the essence of the holographic principle, a bold idea that challenges our understanding of reality itself. Imagine a hologram, a flat, two-dimensional image that, when illuminated, creates the illusion of a three-dimensional object. Now take that concept and apply it to the entire universe. According to the holographic principle, our three-dimensional reality might just be a projection, a kind of cosmic hologram, with all the information about the universe, every star, every planet, every atom stored on a two-dimensional boundary. But how could this work? The answer might lie in the hidden dimensions we've been exploring. Just as a hologram relies on light waves interacting in specific ways to create depth, the holographic universe could depend on the intricate interplay of higher dimensions to project our three-dimensional reality. These hidden layers might act as the framework, the scaffolding, that allows the universe to encode vast amounts of information on a two-dimensional surface and then play it back as the rich, complex world we experience. It's as if the universe is a giant movie, and the screen it's projected on is infinitely thinner than we ever imagined. This idea isn't just a philosophical musing, it has profound implications for physics. For decades, scientists have struggled to reconcile quantum mechanics, which governs the behavior of the very small, with general relativity, which describes the force of gravity on cosmic scales. These two theories work beautifully in their own domains but clash when brought together. The holographic principle offers a potential solution by suggesting that all the information in a volume of space can be encoded on its two-dimensional boundary. It provides a framework where quantum mechanics and gravity might coexist. In this view, gravity isn't a force acting within our three-dimensional world. It's an emergent phenomenon, a byproduct of the way information is encoded and projected from a two-dimensional surface. To make this more relatable, think of a video game. The characters, landscapes, and actions you see on the screen are generated by code lines of information stored in the game's memory. The holographic universe works similarly. The three-dimensional world we experience could be the result of information processing happening on a two-dimensional surface, with hidden dimensions acting as the code that dictates how this information is projected. This perspective not only bridges the gap between quantum mechanics and gravity, but also suggests that the universe operates more like a computational system than we ever realized. What's truly remarkable is how this idea connects to black holes. According to the holographic principle, all the information about matter that falls into a black hole isn't lost. It's encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This resolves the black hole information paradox, a long-standing puzzle in physics, and reinforces the idea that hidden dimensions are essential to understanding the universe's deepest mysteries. As we explore the holographic principle and its connection to hidden dimensions, we're not just redefining our understanding of space and time, we're uncovering a new way to think about reality itself. The universe might not be what it seems, and these hidden layers could hold the key to unlocking its true nature. It's a reminder that sometimes the most profound truths lie not in what we can see, but in what lies just beneath the surface. What if the Big Bang wasn't the beginning of everything, but just the aftermath of a cosmic collision in a higher dimensional space? This is the heart of the Ekpyrotic universe theory, a bold idea that challenges our understanding of how the universe began. Instead of a single explosive event, this theory proposes that our universe emerged from the collision of two Brane's massive, multidimensional structures floating in a higher dimensional realm. It's a concept that reimagines the birth of the cosmos, offering an alternative to the traditional Big Bang narrative. To understand this, let's step back for a moment. In the Ekpyrotic model, our universe isn't an isolated bubble but a three-dimensional brane existing within a larger, higher dimensional space. Picture two sheets of paper floating parallel to each other in a vast, unseen ocean. These sheets represent branes, and when they collide, the energy from that impact creates the conditions for a new universe to form. It's like two cosmic clouds colliding, sparking a chain reaction that births stars, galaxies, and everything we see today. This collision isn't just a one-time event. It's part of a cyclical process, with branes repeatedly approaching, colliding, and then drifting apart, creating new universes each time. What makes this theory so fascinating is how it ties into hidden dimensions. The branes themselves exist in a higher dimensional space, meaning the collision that birthed our universe occurred in a realm beyond our perception. These hidden dimensions aren't just a backdrop, they're essential to the entire process, providing the stage for this cosmic drama to unfold. Without them, the Ekpyrotic model wouldn't work. It's a reminder that the universe's most profound events might be happening in places we can't see, shaped by forces we're only beginning to understand. This idea also offers a fresh perspective on some of the Big Bang theory's biggest puzzles. For example, the cosmic microwave background. The faint glow left over from the early universe shows an astonishing uniformity, as if the entire cosmos was once in perfect thermal equilibrium. But how could distant regions of the universe have reached the same temperature if they were never in contact? The Ekpyrotic model suggests that the collision between branes could have smoothed out the universe, creating the conditions for this uniformity. It's like shaking a snow globe. The initial chaos eventually settles into a balanced, even state. But the Ekpyrotic universe theory doesn't just solve old problems, it opens up thrilling new possibilities. If our universe was born from a collision in higher dimensions, what other universes might exist out there? Could there be countless other branes, each hosting their own cosmos with their own laws of physics? This idea ties into the multiverse concept, suggesting that our universe might be just one of many, each born from its own unique collision. As we explore the Ekpyrotic universe theory, we're not just rethinking the Big Bang, we're reimagining the very nature of cosmic origins. It's a reminder that the universe's story might be far more complex and interconnected than we ever imagined. And as we continue to probe these ideas, we're not just uncovering new chapters in the history of the cosmos, we're rewriting the book altogether. What if the bizarre behavior of particles in the quantum world isn't just random, it's a sign of something deeper, something hidden? Quantum mechanics, the science of the very small, is filled with strange phenomena that defy our everyday intuition. Particles can be in two places at once, communicate instantaneously across vast distances, and even exist in multiple states simultaneously. But what if these mind-bending behaviors aren't just quirks of nature? What if they're clues pointing to the existence of hidden dimensions? One of the most puzzling aspects of quantum mechanics is quantum entanglement, a phenomenon where two particles become so deeply connected that their states are instantly correlated, no matter how far apart they are. Einstein famously called this spooky action at a distance, and for decades scientists have struggled to explain how it works. Hidden dimensions might hold the key. Imagine particles as nodes on a vast, invisible network, with these extra dimensions acting as the hidden wires connecting them. When two particles become entangled, they're not just linked through the three-dimensional space we see, they're interacting through these unseen dimensions, allowing them to communicate in ways that seem instantaneous to us. This idea isn't just a clever metaphor, it's grounded in some of the most cutting-edge theories in physics. For instance, string theory suggests that particles aren't just tiny dots but vibrating strings, and these strings could extend into higher dimensions. In this framework, entanglement might not be so spooky after all. It could simply be the result of particles interacting through a hidden, multidimensional network. It's like two people whispering to each other through a secret tunnel. To an outside observer, the communication seems instantaneous, but in reality, it's happening through a hidden pathway. What's truly fascinating is how this could bridge the gap between quantum mechanics and general relativity, two theories that have long resisted unification. Quantum mechanics governs the behavior of the very small, while general relativity describes the force of gravity on cosmic scales. Hidden dimensions could provide the missing link. If particles are interacting through these extra layers, it might explain why quantum mechanics seems so disconnected from the large-scale structure of the universe. The same hidden dimensions that allow particles to entangle could also influence the way gravity behaves, creating a unified framework that ties everything together. This connection isn't just theoretical, it could have profound implications for our understanding of reality. If hidden dimensions are the key to quantum entanglement, they might also help us solve other quantum mysteries like wave-particle duality or the uncertainty principle. It's as if we've been trying to solve a puzzle with only half the pieces, and these extra dimensions are the missing ones we've been searching for. As we explore the role of hidden dimensions in quantum mechanics, we're not just uncovering new layers of the universe, we're redefining how we think about the very fabric of reality. The quantum world, with all its strangeness, might be a window into a deeper, more interconnected cosmos, one where the boundaries between space, time, and dimensions blur in ways we're only beginning to understand. And as we continue to probe these ideas, we're not just solving scientific puzzles, we're stepping into a hidden world waiting to be discovered. What if the universe's accelerating expansion isn't just a cosmic mystery, it's a clue pointing to the existence of hidden dimensions? Dark energy, the enigmatic force driving this expansion, has puzzled scientists for decades. It makes up about 70% of the universe's energy, yet we know almost nothing about what it is or how it works. But what if the answer lies not in the visible cosmos, but in the unseen layers of reality? What if dark energy is a manifestation of higher dimensional physics, a force leaking into our universe from dimensions we can't perceive? To understand this idea, let's think of dark energy as a hidden engine powering the universe's expansion from behind the scenes. In this analogy, our three-dimensional world is like a car, and dark energy is the unseen motor pushing it forward. But instead of being confined to the car itself, this engine exists in higher dimensions, its influence spilling over into our reality. This could explain why dark energy feels so mysterious. It's not just an invisible force, it's operating in spaces beyond our detection. It's like feeling the vibrations of a machine through a wall, knowing it's there but unable to see it directly. One compelling theory suggests that dark energy might be tied to the geometry of these hidden dimensions. In string theory and Brane world scenarios, the way higher dimensional spaces are shaped could influence how energy and forces behave in our universe. For example, if these extra dimensions are expanding or contracting, they might create a kind of pressure that drives the acceleration of our observable cosmos. It's as if the hidden engine isn't just running, it's also shaping the road we're traveling on, pushing the universe to stretch faster and faster over time. This idea doesn't just solve the puzzle of dark energy, it also connects to one of cosmology's greatest mysteries: why the universe's expansion is accelerating at all. According to Einstein's theory of general relativity, gravity should be slowing down the expansion, pulling galaxies and other structures closer together. Yet, observations show the opposite is happening. Hidden dimensions could provide the missing piece of this puzzle. If dark energy is a higher dimensional force, it might counteract gravity's pull, acting as a kind of cosmic counterbalance that drives the universe to expand. But how do we test such a radical idea? One approach involves looking for subtle clues in the way the universe evolves over time. For instance, if dark energy is linked to higher dimensions, its effects might vary in ways that reveal the presence of these unseen layers. Observing the distribution of galaxies, the behavior of cosmic microwave background radiation, or even the way light bends around massive objects could provide hints about the nature of dark energy and the hidden dimensions it might be connected to. As we explore this connection, we're not just solving a scientific mystery, we're redefining our understanding of the universe's very fabric. Dark energy, once seen as an isolated enigma, might be part of a much larger, multidimensional story. It's a reminder that the cosmos is far more interconnected than we ever imagined, with hidden layers shaping everything from the smallest particles to the largest structures in the universe. And as we continue to probe these ideas, we're not just uncovering new layers of reality, we're stepping into a hidden world waiting to be discovered. What if the particles that make up our universe aren't just confined to the 3 dimensions we know? What if they're interacting with hidden layers of reality, shaping the very fabric of existence in ways we can't see? This is where hidden dimensions take center stage in the world of particle physics, offering a radical new perspective on how the building blocks of the universe behave. Take the Higgs boson, for instance, a particle that gives mass to other particles and is often called the God particle for its fundamental role in the standard model of physics. While we've detected the Higgs boson in experiments like those at the Large Hadron Collider, its behavior still holds mysteries. Some theories suggest that the Higgs might be interacting with extra dimensions, its properties subtly influenced by these unseen layers. It's like a musician in an orchestra whose performance is shaped not just by the instruments around them, but by the acoustics of a hidden concert hall. Imagine the universe as a grand symphony, with particles as the instruments playing their parts. Hidden dimensions could be the unseen acoustics of this cosmic orchestra, shaping how particles vibrate, interact, and even acquire mass. Just as the sound of a violin changes depending on the shape and size of the room it's played in, the behavior of particles like the Higgs boson could be influenced by the geometry of these extra dimensions. In this way, hidden dimensions aren't just passive bystanders, they're active participants, fine-tuning the cosmic performance in ways we're only beginning to understand. But how exactly could this work? One possibility is that particles like the Higgs boson aren't entirely confined to our 3-dimensional world. Instead, they might spill over into higher dimensions, their properties determined by how they interact with these unseen layers. This could explain why the Higgs has the mass it does. Its value isn't arbitrary. It's shaped by the hidden structure of the universe. It's as if the Higgs is playing a duet with these extra dimensions, its behavior a reflection of a larger, more complex reality. This idea isn't just theoretical, it could have profound implications for our understanding of physics. if particles are interacting with hidden dimensions, it might open the door to new discoveries that go beyond the standard model. For instance, we might find evidence of particles that exist only in higher dimensions, or uncover clues about the nature of dark matter and dark energy. These discoveries wouldn't just fill gaps in our knowledge, they could rewrite the rules of physics altogether. What's truly exciting is how this connects to experiments like those at the Large Hadron Collider. If particles are influenced by hidden dimensions, we might detect subtle anomalies in their behavior, tiny deviations from what the standard model predicts. These clues, though faint, could be the first hints of a deeper, multidimensional reality. It's like hearing a faint echo in the concert hall, a whisper of something much larger and more intricate than we ever imagined. As we explore the role of hidden dimensions in particle physics, we're not just uncovering new layers of the universe, we're redefining how we think about the very fabric of reality. The particles we once thought we understood might be part of a much larger cosmic orchestra, their behavior shaped by dimensions we can't yet see. And as we continue to probe these ideas, we're not just solving scientific puzzles, we're stepping into a hidden world waiting to be discovered. What if time travel isn't just the stuff of science fiction, but a real possibility hidden within the fabric of the universe? Hidden dimensions might hold the key to unlocking this extraordinary idea. Imagine time not as a straight line stretching from past to future, but as a complex network of pathways, some of which could loop back on themselves, allowing for travel to the past or future. These loops, known as closed time-like curves, are theoretical constructs that could exist in a universe with extra dimensions. It's like discovering a hidden highway where the rules of time as we know them don't apply. To understand how this might work, let's step into the realm of spacetime, a four-dimensional framework where time is intricately woven with the three spatial dimensions we're familiar with. In this framework, gravity can bend spacetime, creating warps and curves. Now, imagine adding extra dimensions to the mix. These hidden layers could introduce even more complex geometries, allowing for the creation of closed time-like curves. Think of it like a shortcut through a maze. Instead of following the winding paths, you could take a hidden tunnel that loops you back to where you started or even further back in time. The idea of closed time-like curves isn't just speculative. It's grounded in some of the most advanced theories in physics. For instance, in the context of string theory and higher dimensional models, these curves could emerge naturally from the interplay of spacetime and extra dimensions. It's as if the universe has built-in time highways, accessible only if we can navigate the hidden dimensions that make them possible. But how could this revolutionize our understanding of time? For starters, it challenges the linear view of time that dominates our everyday experience. Time might not flow in one direction but could loop, twist, and fold in ways we can't yet perceive. This could open up mind-bending possibilities, like revisiting the past or peeking into the future. It's like realizing that the river of time isn't just a straight current, it's a vast, interconnected network with hidden tributaries and whirlpools. Of course, the implications of this idea are as profound as they are speculative. Closed time-like curves could raise questions about causality, the idea that cause precedes effect. If time loops exist, could someone travel back and change the past, creating paradoxes like the famous grandfather paradox? While these questions remain unanswered, they highlight just how transformative hidden dimensions could be for our understanding of time. As we explore the connection between hidden dimensions and time travel, we're not just reimagining the nature of time. We're stepping into a universe where the boundaries of past, present, and future blur in ways we're only beginning to grasp. The idea that time might be more malleable than we ever imagined is a reminder that reality is far stranger and far more fascinating than it appears. And as we continue to probe these possibilities, we're not just uncovering new layers of the cosmos, we're redefining what it means to exist within it. What if the Big Bang wasn't the beginning of everything, but the result of something happening in dimensions we can't see? This is where hidden dimensions take us into the heart of cosmic origins, offering a radical new perspective on how our universe came to be. Instead of a single explosive event, some theories suggest the Big Bang could have been sparked by a collision between Brane's massive, multidimensional structures floating in a higher dimensional space. It's like imagining the birth of the universe not as a firework igniting in empty space, but as a hidden spark struck in the unseen layers of reality. To visualize this, picture two sheets of paper floating parallel to each other in a vast, invisible ocean. These sheets represent branes, and when they collide, the energy from that impact creates the conditions for a universe to form. In this scenario, the Big Bang wasn't an isolated event. It was the aftermath of a cosmic collision in a higher dimensional realm. It's as if the universe we live in is the echo of that hidden spark, rippling out into the three-dimensional space we know. This idea, known as the Ekpyrotic universe theory, doesn't just offer a new take on the Big Bang, it also ties into the concept of hidden dimensions in a profound way. The branes themselves exist in a higher dimensional space, meaning the collision that birthed our universe occurred in a realm beyond our perception. These extra dimensions aren't just a backdrop, they're essential to the entire process, providing the stage for this cosmic drama to unfold. Without them, the Ekpyrotic model wouldn't work. It's a reminder that the universe's most profound events might be happening in places we can't see, shaped by forces we're only beginning to understand. What makes this theory so compelling is how it addresses some of the Big Bang's biggest puzzles. For instance, the cosmic microwave background. The faint glow left over from the early universe shows an astonishing uniformity, as if the entire cosmos was once in perfect thermal equilibrium. But how could distant regions of the universe have reached the same temperature if they were never in contact? The Ekpyrotic model suggests that the collision between branes could have smoothed out the universe, creating the conditions for this uniformity. It's like shaking a snow globe. The initial chaos eventually settles into a balanced, even state. This idea also opens up thrilling possibilities for the multiverse. If our universe was born from a collision in higher dimensions, what other universes might exist out there? Could there be countless other branes, each hosting their own cosmos with their own laws of physics? It's a perspective that transforms the Big Bang from a singular event into part of a larger, cyclical process, a cosmic dance of branes colliding, separating, and colliding again, giving birth to new universes each time. As we explore the role of hidden dimensions in the Big Bang, we're not just rethinking the origins of the cosmos, we're reimagining the very nature of cosmic beginnings. It's a reminder that the universe's story might be far more complex and interconnected than we ever imagined. And as we continue to probe these ideas, we're not just uncovering new chapters in the history of the cosmos, we're rewriting the book altogether. The cosmic microwave background, or CMB, is often called the afterglow of the Big Bang, a faint, ancient light that fills the universe, carrying secrets from the very beginning of time. But what if this cosmic fingerprint holds more than just the story of our universe's birth? What if it's also a map to something far deeper, hidden dimensions that shape the cosmos in ways we're only starting to understand? When scientists first mapped the CMB, they discovered something surprising. While the background radiation is incredibly uniform, there are tiny fluctuations, small variations in temperature that hint at the seeds of galaxies and galaxy clusters. But some of these fluctuations don't quite fit the standard model of cosmology. They're anomalies, like faint smudges on an otherwise pristine photograph. Could these smudges be evidence of higher dimensional physics at work? One intriguing theory suggests that these anomalies might be the fingerprints of hidden dimensions. Imagine the CMB as a vast cosmic canvas painted with the brushstrokes of the early universe. But beneath this canvas lies another layer, a hidden framework of extra dimensions that subtly influenced how the universe expanded and cooled. These dimensions wouldn't just be passive, they could have left faint imprints on the CMB, like ripples on the surface of a pond revealing the shape of the stones beneath. These imprints might be the key to uncovering the universe's hidden architecture. For instance, some models propose that the early universe experienced rapid expansion or inflation, driven by energy fields in higher dimensions. As these fields interacted with our three-dimensional space, they could have created patterns in the CMB that we're only now beginning to detect. It's like listening to an echo in a vast, empty hall. The sound isn't just coming from the walls you can see, it's also bouncing off hidden surfaces you didn't know were there. But what makes this idea so compelling is how it ties into the origins of the universe itself. If hidden dimensions left their mark on the CMB, they could provide clues about what happened in the moments after the Big Bang or even before it. Were these extra dimensions already there, shaping the universe from its very first breath? Did they influence the way matter and energy were distributed, setting the stage for the cosmic structures we see today? As we study these anomalies, we're not just decoding the CMB, we're peering into the hidden layers of reality itself. The faint smudges on this cosmic canvas might be more than random fluctuations. They could be the signatures of a deeper, multidimensional universe waiting to be uncovered. And as we continue to explore these clues, we're not just unraveling the mysteries of the cosmos. We're stepping into a hidden world, one that could redefine our understanding of everything. What if the galaxies we see scattered across the night sky, the swirling arms of Andromeda, the majestic sombrero, the delicate pinwheel weren't just shaped by the forces we know, but by something far more mysterious? Hidden dimensions, those unseen layers of reality, might have played a crucial role in sculpting the universe's grandest structures, acting as a cosmic artist working behind the scenes. Imagine a sculptor chiseling away at a block of marble, shaping it into a masterpiece. Now, picture the universe itself as that block, and hidden dimensions as the unseen hands guiding the chisel, carving out galaxies and galaxy clusters in ways we're only beginning to understand. One of the most intriguing ideas is that these extra dimensions could influence the distribution of dark matter, the invisible substance that makes up most of the universe's mass. Dark matter doesn't interact with light or ordinary matter, but its gravitational pull is immense, acting as the cosmic glue that holds galaxies together. What if this gravitational influence isn't just confined to the three dimensions we see? What if dark matter is shaped by forces operating in higher dimensions, its presence and behavior subtly guided by these unseen layers? It's as if the sculptor isn't just working with the visible surface of the marble, but is also shaping its hidden interior, creating a structure that's both intricate and interconnected. This idea isn't just speculative, it's grounded in some of the most advanced theories in physics. For instance, in brane-world scenarios, dark matter particles could reside in higher dimensions, their gravitational effects spilling over into our three-dimensional world. This could explain why dark matter seems to clump in certain ways, forming vast cosmic webs that stretch across the universe. These webs, made up of filaments and voids, are like the brushstrokes of a cosmic painting, created by the interplay of dark matter and hidden dimensions. It's a picture of the universe where the visible and the invisible are deeply intertwined, each shaping the other in ways we're only starting to grasp. But how does this relate to the formation of galaxies? Think of galaxies as the stars of the cosmic show, forming within the densest knots of the dark matter web. If hidden dimensions are influencing how dark matter clumps and spreads, they're also indirectly shaping where and how galaxies form. It's like a hidden architect designing the blueprint for a city, determining where the skyscrapers rise and the streets win. In this case, the city is the universe, and the galaxies are its towering landmarks, their positions and movements guided by the unseen hand of higher dimensional physics. This perspective doesn't just solve puzzles, it opens up thrilling possibilities. If hidden dimensions are at work, they could explain why the universe looks the way it does, from the vast cosmic voids to the intricate dance of galaxy clusters. It's a reminder that the cosmos isn't just a random collection of stars and planets. It's a carefully crafted masterpiece shaped by forces both seen and unseen. And as we continue to explore these ideas, we're not just uncovering new layers of the universe, we're stepping into a hidden world waiting to be discovered. So, the next time you gaze up at the night sky, remember, the galaxies you see might not just be the result of gravity and dark matter as we understand them. They could be the product of a deeper, more intricate reality, where hidden dimensions play a crucial role in shaping the cosmos. It's a perspective that transforms the universe from a collection of random structures into a carefully woven tapestry, created by forces we're only beginning to understand. And as we unravel this cosmic mystery, we're not just studying the stars, we're uncovering the hidden hands that shape them. What if the tiniest particles in the universe hold the biggest secrets? Neutrinos, ghostly, nearly massless particles that barely interact with matter, are some of the most mysterious entities in physics. They're so elusive that trillions of them pass through your body every second without you ever noticing. But what if their strange behavior isn't just a quirk of nature? What if it's a clue pointing to the existence of hidden dimensions? Imagine a dance floor where most particles move in predictable patterns, locked into the rhythm of the three dimensions we know. Neutrinos, on the other hand, seem to be dancing to a different tune, one that's hidden from view. This hidden dance could be a sign that neutrinos are interacting with extra dimensions, their movements influenced by forces we can't directly observe. It's as if these particles are stepping in and out of unseen layers of reality, their behavior shaped by a cosmic choreography happening beyond our perception. This idea isn't just poetic, it could solve one of the biggest puzzles in particle physics: why neutrinos have such tiny masses. According to the standard model, neutrinos should be massless, yet experiments show they have a small but measurable mass. Hidden dimensions might hold the answer. If neutrinos are interacting with these extra layers, their mass could be a side effect of their multidimensional existence. It's like a ballerina whose graceful movements are influenced by the hidden mechanics of the stage beneath her feet. The extra dimensions aren't just a backdrop, they're an active part of the performance, subtly shaping how neutrinos behave. But how does this work in practice? One theory suggests that neutrinos could be leaking into higher dimensions, their mass and properties influenced by how they interact with these unseen spaces. In this scenario, the tiny mass we observe in our three-dimensional world might just be a fraction of their true mass, with the rest spread out across the extra dimensions. It's as if we're seeing only the tip of the iceberg, with the bulk of the neutrinos' mass hidden in a realm we can't access. This idea could also explain why neutrinos are so hard to detect. If they're moving through extra dimensions, they might only occasionally step into our observable universe, making them appear fleeting and elusive. It's like trying to catch a shadow on a wall. You know it's there, but it's always just out of reach. What's truly fascinating is how this connects to one of the biggest questions in physics: how to unify the standard model with gravity. Neutrinos, with their strange behavior and potential ties to hidden dimensions, might be the missing link. If their mass and interactions are influenced by higher dimensional physics, they could provide a bridge between the quantum world and the cosmos, helping us understand how gravity fits into the larger picture. As we explore the mystery of neutrinos and their connection to hidden dimensions, we're not just solving a puzzle, we're uncovering a deeper, more interconnected reality. These ghostly particles, once seen as anomalies, might be the key to understanding the universe's hidden layers. And as we continue to probe their secrets, we're not just studying particles, we're stepping into a hidden world waiting to be discovered. What if the recipe for life itself was written in the hidden dimensions of the universe? Imagine a chef crafting a perfect dish, carefully measuring each ingredient to create a delicate balance of flavors. Now picture the universe as that chef, and the fundamental constants of nature like the strength of gravity or the charge of an electron as the ingredients. These constants are the building blocks of reality, finely tuned to allow atoms to form, stars to shine, and ultimately, life to emerge. But what if this fine-tuning isn't just luck? What if hidden dimensions played a role in setting these constants, like a secret recipe guiding the cosmic kitchen? This idea isn't just speculative, it's grounded in some of the most fascinating theories in physics. Extra dimensions could influence the fundamental forces and particles that shape our universe, subtly tweaking their properties in ways that make life possible. For instance, if gravity were slightly stronger or weaker, stars might not form, and without stars, there would be no planets, no chemistry, and no life. The same goes for other constants, like the strength of the electromagnetic force or the mass of the proton. These values aren't arbitrary, they're precisely calibrated to allow the universe to evolve in a way that supports complexity. So, how might hidden dimensions fit into this? One theory suggests that the geometry of these extra layers could determine the values of these constants. Think of it like a hidden dial, adjusting the settings of the universe as it unfolds. If these dimensions are shaped in just the right way, they could create the conditions needed for life to arise. It's as if the universe has a built-in recipe, with hidden dimensions acting as the secret spices that make everything come together perfectly. This idea also ties into the concept of the fine-tuned universe, a long-standing puzzle in cosmology. Why do the fundamental constants have the exact values they do? If they were even slightly different, the universe as we know it wouldn't exist. Some scientists argue that this fine-tuning is evidence of a multiverse, where countless universes exist, each with its own set of constants. In this view, our universe is just one of many with the right ingredients for life. But hidden dimensions offer another possibility, that the fine-tuning isn't random but the result of a deeper, multidimensional structure shaping the cosmos. What's truly remarkable is how this connects to the evolution of life itself. From the formation of the first atoms to the emergence of complex organisms, every step in life's journey depends on the precise balance of these constants. Hidden dimensions could be the unseen hand guiding this process, ensuring that the universe evolves in a way that allows life to flourish. It's a perspective that transforms the story of life from a series of lucky accidents into a carefully orchestrated cosmic dance, choreographed by forces we're only beginning to understand. As we explore the role of hidden dimensions in the evolution of life, we're not just uncovering the secrets of the universe, we're redefining our place within it. The idea that these unseen layers might have shaped the very conditions that allowed life to emerge is a reminder of how interconnected everything is, from the tiniest particles to the vastness of the cosmos. And as we continue to probe these mysteries, we're not just studying the origins of life, we're stepping into a hidden world, one that might hold the key to understanding our existence. What if the seemingly empty space around us isn't empty at all, but filled with a mysterious energy that's shaping the destiny of the universe? This energy, known as vacuum energy, is one of the most puzzling phenomena in physics. It's the energy of empty space itself, a kind of cosmic hum that permeates every corner of existence. Yet, despite its ubiquity, we know almost nothing about where it comes from or why it has the value it does. But what if the answer lies in the hidden dimensions we've been exploring? What if vacuum energy is a shadow cast by forces operating in higher dimensional spaces? To grasp this idea, let's think of vacuum energy as a hidden reservoir, a vast, unseen store of power that's always present but rarely noticed. In this analogy, our three-dimensional world is like the surface of a lake, with ripples and waves representing the particles and forces we can observe. But beneath the surface lies something far deeper, a reservoir of energy that's constantly influencing the lake's behavior. In the same way, hidden dimensions could act as the source of vacuum energy, their unseen dynamics shaping the very fabric of space-time. It's as if the universe has a hidden engine, quietly powering everything from the smallest quantum fluctuations to the largest cosmic structures. This connection between vacuum energy and hidden dimensions isn't just a fascinating idea, it could solve one of cosmology's greatest mysteries: why the observed value of vacuum energy is so incredibly small. According to quantum field theory, vacuum energy should be enormous, far larger than what we actually measure. This discrepancy, known as the cosmological constant problem, has baffled scientists for decades. But if vacuum energy is influenced by higher dimensional physics, its value might be much smaller because it's being diluted across these extra layers. Imagine pouring a bucket of water into a vast ocean. The water is still there, but its presence is barely noticeable. In the same way, vacuum energy could be spread out across hidden dimensions, making it appear faint in our observable universe. What's truly exciting is how this idea ties into the accelerating expansion of the universe. Vacuum energy is thought to be the driving force behind this expansion, acting as a kind of cosmic pressure that pushes galaxies apart. If hidden dimensions are shaping vacuum energy, they're also indirectly shaping the fate of the cosmos. It's a reminder that the universe's most profound mysteries, from the tiniest quantum fluctuations to the largest cosmic structures, might all be connected by these unseen layers of reality. As we explore the mystery of vacuum energy and its connection to hidden dimensions, we're not just solving a scientific puzzle, we're uncovering a deeper, more interconnected reality. The energy of empty space, once seen as an isolated enigma, might be part of a much larger story, one that stretches across dimensions we can't yet see. And as we continue to probe these ideas, we're not just studying the cosmos, we're stepping into a hidden world waiting to be discovered. What if extraterrestrial life isn't just out there in the stars, but right here, hidden in dimensions we can't see? The search for life beyond Earth has always been a quest to look outward, scanning distant planets, analyzing atmospheric compositions, and listening for signals from faraway civilizations. But what if the answer isn't just across the vastness of space? What if it's also hiding in the unseen layers of reality, in dimensions beyond our perception? Imagine our universe as a vast, sprawling garden. We're familiar with the plants and flowers. We can see the ones rooted in the soil of our three-dimensional world. But what if there's another garden, just as lush and vibrant, growing in a hidden corner we can't access? This hidden garden could be teeming with life, thriving in higher dimensions, completely invisible to us. Life in these dimensions might not even resemble what we know. It could be composed of particles or energy forms that don't interact with our three-dimensional world, making it impossible for us to detect with our current tools. This idea isn't just speculative, it's grounded in some of the most intriguing theories in physics. For instance, if life exists in higher dimensions, it might operate under entirely different physical laws. The chemistry, biology, and even the concept of life itself could be so alien that we wouldn't recognize it even if we stumbled across it. It's like trying to describe color to someone who's never seen it. The very framework for understanding might be missing. But how does this change our approach to finding extraterrestrial life? For one, it forces us to think beyond the traditional methods of searching for biosignatures or listening for radio signals. If life exists in hidden dimensions, we might need entirely new technologies and approaches to detect it. Imagine trying to find a fish in a lake by only looking at the surface. You'd miss the entire underwater world. Similarly, our current tools might be blind to life forms that exist in higher dimensions. This also raises fascinating questions about the nature of life itself. Could life evolve in higher dimensions, adapting to conditions we can't even imagine? If so, what would it look like? Would it be energy-based or composed of particles that don't exist in our three-dimensional world? These questions challenge our assumptions about what life is and where it can exist, expanding the boundaries of possibility. And here's where it gets even more intriguing. If life in higher dimensions is real, it might not just be microbial. Entire civilizations could exist in these unseen layers, their cities and technologies completely invisible to us. They might be observing us, studying our three-dimensional world without us ever knowing. It's a humbling thought, one that transforms the search for extraterrestrial life from a quest to find distant neighbors into an exploration of the very fabric of reality itself. As we continue to probe the mysteries of hidden dimensions, we're not just redefining our understanding of the universe, we're reimagining the search for life. The idea that extraterrestrial life might exist in dimensions beyond our perception is a reminder that the cosmos is far stranger and far more interconnected than we ever imagined. And as we explore these possibilities, we're not just searching for life, we're uncovering a hidden world waiting to be discovered. What if the key to one of physics' greatest puzzles lies in the hidden dimensions of the universe? For decades, scientists have struggled to reconcile two of the most successful theories in science: quantum mechanics, which governs the behavior of the very small, and general relativity, which describes the force of gravity on cosmic scales. These two frameworks work beautifully in their own domains, but when brought together, they clash in ways that defy explanation. Enter hidden dimensions, a concept that might just provide the missing link between these seemingly incompatible worlds. Imagine quantum mechanics and gravity as two cities separated by a vast canyon. Each city thrives on its own, with its own rules and rhythms, but there's no way to travel between them. Hidden dimensions could act as a bridge, connecting these two realms in ways we're only beginning to understand. This bridge isn't just a metaphor, it's a theoretical framework where the vibrations of strings in higher dimensions could explain both the quantum behavior of particles and the curvature of spacetime described by gravity. It's as if we've been looking at two sides of the same coin, unaware that the coin itself exists in a higher dimensional space. One of the most promising ideas in this area is string theory, which suggests that particles aren't just tiny dots but vibrating strings. These strings don't just move in the three dimensions we know, they dance across higher dimensional spaces, their vibrations producing the particles and forces we observe. In this framework, gravity isn't a separate force but a natural consequence of how these strings interact in higher dimensions. It's like discovering that the bridge between the two cities isn't just a physical connection, it's the very fabric that holds both worlds together. But how does this solve the problem of quantum gravity? The answer lies in how hidden dimensions could smooth out the contradictions between the two theories. In our three-dimensional world, gravity is described as the curvature of spacetime, while quantum mechanics deals with discrete particles and probabilities. Hidden dimensions offer a way to blend these concepts, providing a space where gravity can emerge naturally from the quantum behavior of strings. It's as if the canyon between the two cities isn't just crossed, it's filled in, creating a seamless landscape where both theories can coexist. This idea isn't just theoretical, it could have profound implications for our understanding of the universe. If hidden dimensions are the key to unifying quantum mechanics and gravity, they might also help us solve other mysteries, like the nature of black holes or the origin of dark energy. It's a reminder that the universe's deepest puzzles might not be separate challenges but pieces of a larger, interconnected puzzle, one that's waiting to be solved. As we explore the mystery of quantum gravity and its connection to hidden dimensions, we're not just bridging two theories, we're uncovering a deeper, more unified reality. The idea that the cosmos operates on a multidimensional stage, where the forces of nature are woven together by invisible threads, is both humbling and exhilarating. And as we continue to probe these ideas, we're not just solving scientific puzzles, we're stepping into a hidden world, one that holds the key to understanding the very fabric of existence. What if consciousness, the very essence of who we are, isn't confined to the three-dimensional world we experience every day? What if it's shaped by forces and dimensions we can't see? This isn't just a philosophical question. It's a possibility that some of the most daring theories in physics and neuroscience are beginning to explore. Hidden dimensions, those unseen layers of reality we've been delving into, might not just influence the physical universe, they could also play a role in the nature of consciousness itself. Imagine consciousness as a reflection in a mirror. In our everyday experience, we see only the surface of the mirror, the thoughts, emotions, and perceptions that make up our mental landscape. But what if the mirror is just the tip of the iceberg? What if the true nature of consciousness lies in the hidden dimensions behind the glass, where deeper layers of reality shape and influence what we see on the surface? This idea suggests that our minds might be far more complex and interconnected than we ever imagined, with hidden dimensions acting as the unseen framework that supports and shapes our experience of reality. One intriguing theory proposes that consciousness could be a higher dimensional phenomenon. In this view, the brain isn't just a three-dimensional organ processing information. It's a kind of receiver, tuning into higher dimensional signals that give rise to our thoughts, emotions, and sense of self. It's like a radio picking up invisible waves. What we perceive as consciousness might be the result of interactions happening in dimensions we can't directly observe. This doesn't just challenge our understanding of the mind, it opens up the possibility that consciousness is a fundamental part of the universe, woven into the fabric of reality itself. But how could this work? One way to think about it is through the concept of neural networks. In our brains, billions of neurons are constantly firing, creating the complex patterns of activity that give rise to consciousness. Now, imagine if these networks aren't just confined to the physical structure of the brain, but extend into higher dimensions. The connections between neurons might exist not just in the three-dimensional space of the brain, but in these unseen layers, creating a multidimensional web of thought and awareness. It's as if the mind is a vast, multidimensional tapestry, with each thread representing a different aspect of consciousness, woven together by forces we're only beginning to understand. This idea isn't just speculative, it has profound implications for how we think about the mind and its place in the universe. If consciousness is influenced by hidden dimensions, it could explain some of the most puzzling aspects of human experience, from intuition and creativity to phenomena like near-death experiences or altered states of awareness. These experiences might not be anomalies, they could be glimpses into a deeper, multidimensional reality, where the boundaries between the mind and the cosmos blur. What's truly fascinating is how this connects to the broader questions we've been exploring. From the behavior of particles to the structure of the cosmos, hidden dimensions seem to play a role in shaping the universe at every level. Could consciousness be another piece of this puzzle, a phenomenon that emerges from the interplay of higher dimensional forces? If so, it would revolutionize not just our understanding of the mind, but also our place in the universe. We wouldn't just be observers of reality, we'd be active participants, our thoughts and perceptions shaped by the hidden layers of existence. As we explore the role of hidden dimensions in consciousness, we're not just redefining the nature of the mind, we're uncovering a deeper, more interconnected reality. The idea that our thoughts and awareness might be influenced by forces beyond our perception is both humbling and exhilarating. It's a reminder that the universe is far stranger and far more beautiful than we ever imagined. And as we continue to probe these ideas, we're not just studying the mind, we're stepping into a hidden world waiting to be discovered. What if the flow of time, the relentless march from past to future, isn't just a feature of our universe but a clue to its hidden structure? Time, as we experience it, moves in one direction like an arrow flying forward. But why does it flow this way? Why can we remember the past but not the future? This is the mystery of the arrow of time, and hidden dimensions might hold the key to unraveling it. Imagine time as a river winding its way through the landscape of the universe. In our everyday experience, we're carried along by its current, moving inexorably from the past to the future. But what if this river has hidden tributaries, extra dimensions that influence its flow? These unseen layers could be shaping the asymmetry of time, determining why it moves in one direction and not the other. It's as if the river we see is just the surface, while beneath it lies a vast, interconnected network of currents, each one subtly guiding time's journey. This idea isn't just poetic, it's rooted in some of the most profound theories in physics. For instance, in certain models of string theory, the arrow of time could be linked to the geometry of hidden dimensions. These extra layers might create a kind of temporal landscape, where the flow of time is influenced by the way these dimensions are shaped. Think of it like a river flowing over a rocky bed. The shape of the rocks determines the speed and direction of the water. In the same way, the geometry of hidden dimensions could determine how time flows in our observable universe. But how does this explain the one-way direction of time? One possibility lies in the concept of entropy, the measure of disorder in a system. In our universe, entropy always increases, creating the arrow of time we experience. But hidden dimensions could play a role in setting the initial conditions for this increase, like a hidden hand tipping the scales toward disorder. It's as if the river of time starts at a high point, with entropy acting as gravity, pulling it downhill in one direction. This perspective doesn't just solve a scientific puzzle, it challenges our understanding of time itself. If hidden dimensions are influencing the arrow of time, it means that time isn't just a passive backdrop to the universe. It's an active, dynamic force shaped by the unseen structure of reality. It's a reminder that the flow of time might not be as simple as it seems, and that the universe's deepest mysteries are often hidden in plain sight. As we explore the connection between hidden dimensions and the arrow of time, we're not just uncovering new layers of the cosmos, we're redefining how we think about the very nature of existence. The idea that time's flow might be shaped by forces we can't see is both humbling and exhilarating. And as we continue to probe these mysteries, we're not just studying time, we're stepping into a hidden world, one that holds the key to understanding the universe's most fundamental rhythms. What if everything we perceive as reality is nothing more than a projection, a cosmic shadow cast by a higher dimensional world? This isn't just a wild thought experiment. It's a serious idea that some of the most groundbreaking theories in physics are beginning to explore. Hidden dimensions, those unseen layers of reality, might be the key to understanding what's truly going on behind the scenes of our universe. Imagine reality as a grand theatrical performance. We're the audience watching the actors move across the stage, completely engrossed in the story unfolding before us. But what if the stage we see is just a fraction of the full production? What if the real drama is happening backstage in higher dimensions, and what we experience is merely a projection of that deeper reality? This is the essence of the holographic principle, a theory that suggests our three-dimensional universe might be a kind of hologram, a two-dimensional surface encoding all the information about the cosmos. In this view, hidden dimensions act like the hidden stage, the unseen framework where the true actors of reality are performing. The particles, forces, and even the flow of time we experience in our world could be projections of interactions happening in these higher dimensional spaces. It's as if we've been watching a movie on a flat screen, unaware that the real story is unfolding in a three-dimensional theater just beyond our view. But how could this work? Think of a shadow puppet show. The puppeteer's hands move in 3 dimensions, creating intricate shapes on a 2-dimensional wall. To the audience, the shadows are the reality, but they're only a simplified version of the full, multidimensional performance. In the same way, our universe might be a shadow of a higher dimensional reality, with hidden dimensions shaping the shadows we perceive as particles, forces, and even the passage of time. This idea doesn't just challenge our understanding of reality, it could revolutionize it. If our universe is a projection from higher dimensions, it means that everything we see, touch, and experience is just the surface of something far deeper and more complex. The laws of physics, the behavior of particles, and even the nature of consciousness might all be shaped by these unseen layers. It's a perspective that transforms the universe from a collection of isolated phenomena into a unified, multidimensional tapestry. What makes this idea so compelling is how it connects to some of the biggest questions in physics. For instance, the holographic principle could help resolve the black hole information paradox, a puzzle about what happens to information that falls into a black hole. If all the information about the universe is encoded on a 2-dimensional surface, like a cosmic hard drive, then nothing is truly lost. It's just stored in a way we can't yet access. Hidden dimensions could provide the framework for this encoding, acting as the bridge between the 2-dimensional surface and the 3-dimensional world we experience. As we explore the role of hidden dimensions in the nature of reality, we're not just uncovering new layers of the cosmos, we're redefining what it means to exist within it. The idea that our universe might be a projection from higher dimensions is both humbling and exhilarating. It's a reminder that reality, as we know it, might just be the tip of an unimaginably vast iceberg with hidden depths waiting to be explored. And as we continue to probe these mysteries, we're not just studying the universe, we're stepping into a hidden world, one that could reshape our understanding of existence itself. The fine structure constant. It's a number so precise, so fundamental, that it seems almost too perfect to be random. This dimensionless constant, roughly equal to 1/137, governs the strength of the electromagnetic force, dictating how particles interact and atoms form. It's a cornerstone of our universe, yet its value remains one of physics' greatest puzzles. Why does it have this specific number, and could hidden dimensions hold the key to understanding its mysterious precision? Imagine the fine structure constant as a dial on a cosmic control panel, finely tuned to just the right setting to allow stars to burn, atoms to bond, and life to emerge. But what if this dial isn't just sitting in our 3-dimensional world? What if it's connected to hidden dimensions, its value subtly adjusted by forces operating in realms we can't see? This isn't just a fanciful idea. It's a serious possibility explored by some of the most cutting-edge theories in physics. Extra dimensions could act like invisible gears, turning the dial of the fine structure constant and setting it to the precise value needed for our universe to function. One compelling theory suggests that the fine structure constant might not be constant at all, at least not across all dimensions. In higher dimensional spaces, the strength of the electromagnetic force could vary, influenced by the geometry of these unseen layers. When this force spills over into our three-dimensional world, it averages out to the value we observe. It's like hearing a single note in a symphony. The harmony of higher dimensions shapes the sound, even if we can't hear the full orchestra. This idea could solve one of physics' most profound mysteries: why the fundamental constants of nature are so finely tuned. If the fine structure constant is influenced by hidden dimensions, its value isn't arbitrary. It's the result of a deeper, multidimensional structure shaping the universe. It's as if the cosmos has a hidden blueprint, written in the language of higher dimensional geometry, that ensures everything from the tiniest particles to the largest structures falls into place perfectly. But how do we test such a radical idea? One approach involves looking for subtle variations in the fine structure constant over time or across space. If extra dimensions are influencing its value, we might detect tiny fluctuations that reveal their presence. These clues, though faint, could be the first hints of a deeper, more interconnected reality. The mystery of the fine structure constant isn't just a scientific puzzle, it's a window into the hidden layers of the universe. By exploring how extra dimensions might shape this fundamental constant, we're not just solving a mystery, we're uncovering the deeper architecture of reality itself. And as we continue to probe these ideas, we're stepping into a world where the boundaries between the seen and the unseen blur, revealing a cosmos far more intricate and far more beautiful than we ever imagined. What if the very fabric of space-time, the stage on which the universe unfolds, isn't as simple as it seems? We often think of space-time as a smooth, four-dimensional canvas with 3 dimensions of space and 1 of time. But what if this canvas is just the surface of something far more intricate? What if hidden dimensions are subtly warping and shaping space-time in ways we can't yet detect, like a hidden hand sculpting the unseen layers of reality? Imagine space-time as a piece of fabric stretched out across a table. From our perspective, the fabric looks flat and uniform, but what if there's more to it? Beneath the surface, the fabric could be folded, twisted, or even threaded with tiny, hidden fibers, extra dimensions that influence its shape and behavior. These unseen layers might not be visible to us, but their effects could ripple through the fabric, subtly altering how space-time behaves on the largest and smallest scales. This idea isn't just a metaphor, it's a central theme in some of the most advanced theories in physics. For instance, in string theory and brane world scenarios, hidden dimensions could create tiny wrinkles in space-time, influencing everything from the motion of planets to the behavior of particles. These wrinkles might be too small to detect directly, but their cumulative effects could explain some of the universe's most puzzling phenomena. For example, the way galaxies rotate or how light bends around massive objects might be subtly influenced by these hidden layers, like ripples on the surface of a pond revealing the shape of the stones beneath. But how exactly could hidden dimensions warp space-time? One possibility is that these extra layers introduce new kinds of curvature, bends, and folds in the fabric of reality that go beyond the 4 dimensions we know. This curvature could create pathways or shortcuts through space-time, like tunnels hidden within the folds of the fabric. It's as if the universe has built-in shortcuts, allowing particles or even entire galaxies to traverse vast distances in ways that seem impossible from our 3-dimensional perspective. This idea also ties into one of the biggest mysteries in physics, the nature of gravity. In our observable universe, gravity is described by the curvature of space-time, as Einstein's theory of general relativity explains. But if hidden dimensions are warping space-time in ways we can't see, they could be influencing gravity on a deeper level. For instance, the weakness of gravity compared to the other fundamental forces might be due to its leakage into these extra dimensions, spreading its influence across a larger, multidimensional space. What's truly fascinating is how this could change our understanding of the universe. If hidden dimensions are shaping space-time, they could be the key to unlocking some of cosmology's greatest puzzles, from the nature of dark matter to the origins of the Big Bang. It's a perspective that transforms space-time from a static backdrop into a dynamic, multidimensional structure, full of hidden twists and turns waiting to be discovered. As we explore the role of hidden dimensions in the nature of space-time, we're not just uncovering new layers of the cosmos, we're redefining how we think about the very fabric of reality. The idea that space-time might be far more complex and interconnected than we ever imagined is both humbling and exhilarating. And as we continue to probe these mysteries, we're stepping into a hidden world, one that could reshape our understanding of existence itself. What if the universe's accelerating expansion, a phenomenon that has baffled scientists for decades, isn't just a random cosmic quirk, but the result of forces operating in dimensions we can't see? At the heart of this mystery lies the cosmological constant, a term introduced by Einstein and later revived to describe the mysterious energy driving the universe's expansion. But what if this energy isn't confined to the three-dimensional space we know? What if it's a shadow cast by hidden dimensions, a kind of cosmic engine humming in the background, powering the universe's growth from realms beyond our perception? Imagine the universe as a car speeding down an endless highway. The cosmological constant is the engine, quietly pushing the car forward faster and faster. But here's the twist: this engine isn't under the hood. It's hidden in a higher dimensional garage, its influence spilling over into our observable universe. This isn't just a poetic metaphor, it's a serious possibility explored by some of the most advanced theories in physics. Hidden dimensions could act as the source of this mysterious energy, their unseen dynamics shaping the very fabric of space-time and driving the universe's expansion. One way to think about this is through the lens of vacuum energy, the energy of empty space itself. In our three-dimensional world, vacuum energy is incredibly faint, yet it's thought to be the driving force behind the cosmological constant. But why is its value so small? Some theories suggest that vacuum energy isn't weak. It's just spread thin, diluted across extra dimensions. It's like pouring a bucket of water into a vast ocean. The water is still there, but its presence is barely noticeable. In the same way, the cosmological constant might appear faint in our universe because it's being shared across higher dimensional spaces. This idea doesn't just solve the puzzle of the cosmological constant. It could also help resolve one of cosmology's greatest mysteries: why the universe's expansion is accelerating at all. According to Einstein's theory of general relativity, gravity should be slowing down the expansion, pulling galaxies and other structures closer together. Yet, observations show the opposite is happening. Hidden dimensions could provide the missing piece of this puzzle. If the cosmological constant is a higher dimensional force, it might counteract gravity's pull, acting as a kind of cosmic counterbalance that drives the universe to expand. But how do we test such a radical idea? One approach involves looking for subtle clues in the way the universe evolves over time. For instance, if the cosmological constant is linked to higher dimensions, its effects might vary in ways that reveal the presence of these unseen layers. Observing the distribution of galaxies, the behavior of cosmic microwave background radiation, or even the way light bends around massive objects could provide hints about the nature of this mysterious energy and the hidden dimensions it might be connected to. As we explore the connection between the cosmological constant and hidden dimensions, we're not just solving a scientific puzzle, we're uncovering a deeper, more interconnected reality. The energy driving the universe's expansion, once seen as an isolated enigma, might be part of a much larger, multidimensional story. It's a reminder that the cosmos is far more interconnected than we ever imagined, with hidden layers shaping everything from the smallest particles to the largest structures in the universe. And as we continue to probe these ideas, we're not just studying the universe, we're stepping into a hidden world, one that could reshape our understanding of existence itself. Light, the very essence of our visual world, is one of the most fundamental forces in the universe. But what if its behavior isn't just governed by the three dimensions we know? What if hidden dimensions are subtly shaping the way light moves, bends, and interacts? This idea isn't just a flight of fancy, it's a serious possibility explored by some of the most intriguing theories in physics. Hidden dimensions could be the key to unlocking new mysteries about light, from its polarization to the way it travels through space. Think of light as a beam passing through a prism. In our familiar three-dimensional world, the prism splits the light into its constituent colors, creating a rainbow. But what if there's a hidden prism, one that exists in extra dimensions, subtly altering the light in ways we can't directly see? This hidden prism could influence the polarization of light, the orientation of its waves, or even the way it interacts with matter. Just as a prism bends light into a spectrum, these extra dimensions might be bending the very nature of light itself, creating effects that go beyond our current understanding. One way this could work is through the geometry of hidden dimensions. If light interacts with these extra layers, its behavior might be subtly influenced by their shape and structure. For instance, polarized light, where the waves vibrate in a specific direction, could be a result of light interacting with higher dimensional spaces. It's like a dancer moving through a room full of hidden obstacles. Their steps might look smooth from one angle, but they're being subtly guided by forces we can't see. This idea doesn't just explain existing phenomena, it opens up thrilling new possibilities. If light is influenced by hidden dimensions, it could help us understand why certain properties of light, like polarization, seem so precise and consistent. These extra layers might act as a kind of cosmic tuning fork, ensuring that light behaves in ways that allow us to see the universe clearly. It's as if the hidden dimensions are the unseen stagehands, adjusting the lighting to create the perfect cosmic performance. But how does this change our understanding of light? For centuries, we've thought of light as a wave or a particle, governed by the laws of electromagnetism. If hidden dimensions are in play, light might be far more complex, a multidimensional phenomenon that we're only beginning to grasp. This could revolutionize fields like optics, telecommunications, and even quantum computing, where the precise control of light is crucial. What's truly fascinating is how this connects to the broader questions we've been exploring. From the nature of gravity to the origins of the universe, hidden dimensions seem to play a role in shaping reality at every level. Light, with its dual nature and mysterious properties, could be the next piece of this cosmic puzzle. As we continue to probe these ideas, we're not just studying light, we're uncovering a deeper, more interconnected reality, one where the hidden layers of existence shape everything from the smallest photon to the vast expanse of the cosmos. So, the next time you see a beam of sunlight or the glow of a distant star, remember, the light you're witnessing might not just be a product of the world we see. It could be a glimpse into a hidden dimension, a subtle reminder that reality is far more intricate and far more beautiful than we ever imagined. The Higgs field, it's the invisible force that gives particles their mass, the cosmic sculptor shaping the very building blocks of the universe. But what if this field isn't just confined to the three dimensions we know? What if it's being shaped by hidden dimensions, like a sculptor working behind an unseen curtain, molding the universe in ways we can't directly observe? This idea isn't just a wild thought, It's a serious possibility explored by some of the most cutting-edge theories in physics, and it could hold the key to solving one of particle physics' greatest mysteries. Imagine the Higgs field as a vast, invisible ocean filling every corner of the universe. Particles, like tiny boats floating on this ocean, gain mass by interacting with it. But what if this ocean isn't just a flat, featureless expanse? What if it's rippling and swirling, influenced by hidden currents flowing through extra dimensions? In this scenario, the Higgs field isn't just a passive backdrop, it's an active participant. Its behavior shaped by the unseen geometry of higher dimensional spaces. These hidden dimensions could act like a sculptor's hands, subtly shaping the field and, in turn, determining the masses of particles in our observable universe. This idea isn't just theoretical, it could explain one of the biggest puzzles in physics: why the Higgs boson, the particle associated with the Higgs field, has the mass it does. According to the standard model, the Higgs boson should be much heavier than what we've observed. But if hidden dimensions are influencing the Higgs field, they could be fine-tuning its mass, like a hidden dial adjusting the settings of the universe. It's as if the Higgs boson isn't just a product of our three-dimensional world, it's a reflection of a deeper, multidimensional reality, shaped by forces we can't yet see. What's truly fascinating is how this connects to the broader mystery of mass itself. Why do particles have the masses they do? Why is the electron so much lighter than the proton? Hidden dimensions could provide the answer. If the Higgs field is influenced by higher dimensional spaces, the masses of particles might not be arbitrary. They could be the result of a complex interplay between the Higgs field and these unseen layers. It's like discovering that the weights of objects aren't random but determined by a hidden set of scales, calibrated by the geometry of extra dimensions. This perspective doesn't just solve puzzles, it opens up thrilling possibilities. If the Higgs field is connected to hidden dimensions, it could provide a pathway to discovering these extra layers. Experiments at the Large Hadron Collider, for instance, might detect subtle anomalies in the behavior of the Higgs boson, offering clues about the existence of higher dimensional spaces. These clues, though faint, could be the first hints of a deeper, more interconnected reality. As we explore the mystery of the Higgs field and its connection to hidden dimensions, we're not just uncovering new layers of the universe, we're redefining how we think about mass, particles, and the very fabric of reality. The idea that the Higgs field might be shaped by forces beyond our perception is both humbling and exhilarating. It's a reminder that the universe's deepest secrets might not be hidden in the stars or the depths of atoms. They might be lurking in the unseen dimensions that shape everything we know. And as we continue to probe these ideas, we're not just studying particles, we're stepping into a hidden world, one that could rewrite the story of existence itself. What if the matter we see around us, the atoms, molecules, and particles that make up everything from stars to our own bodies, is just the surface of something far deeper? Hidden dimensions, those unseen layers of reality, might not just influence the forces and energy of the universe, they could also shape the very nature of matter itself. Imagine matter as a tapestry woven from threads of particles and forces. From our perspective, the tapestry appears flat and two-dimensional. But what if there's a hidden third dimension, a depth we can't see, where the true complexity of matter is revealed? This idea isn't just an abstract thought experiment, it's a serious possibility explored by some of the most advanced theories in physics. For instance, string theory suggests that particles aren't just tiny dots but vibrating strings, and these strings could extend into higher dimensions. In this framework, the properties of matter, its mass, charge, and even its interactions might be determined by how these strings vibrate across these unseen layers. It's as if the tapestry of matter isn't just a flat image but a multidimensional sculpture, with hidden dimensions shaping its form and structure in ways we're only beginning to understand. One of the most intriguing implications of this idea is its connection to dark matter. This mysterious substance makes up about 85% of the matter in the universe, yet it doesn't interact with light or ordinary matter in any way we can detect. But what if dark matter isn't just invisible, it's existing in higher dimensions, its presence felt only through its gravitational influence in our three-dimensional world? In this scenario, dark matter could be like the hidden threads of the tapestry, unseen but essential to the overall design. These higher dimensional particles might interact with our observable universe only through gravity, explaining why dark matter is so elusive. It's a perspective that transforms dark matter from a cosmic mystery into a clue pointing to the existence of hidden dimensions. But how does this change our understanding of matter as a whole? If particles can exist in higher dimensions, it means the matter we see is just a fraction of what's truly out there. The protons, neutrons, and electrons that make up atoms could be part of a much larger, multidimensional reality. This doesn't just deepen the mystery of matter, it opens up thrilling possibilities. For instance, could there be entire forms of matter that exist only in higher dimensions, completely invisible to us? Could these hidden particles be the key to unlocking new technologies or even new forms of energy? This idea also challenges our perception of the universe's structure. If matter isn't confined to the three dimensions we know, it means the cosmos is far more interconnected than we ever imagined. The atoms that make up a star or a planet might be linked to higher dimensional spaces, their properties and behaviors influenced by forces we can't directly observe. It's as if the universe isn't just a collection of isolated objects, but a vast, multidimensional network, with hidden dimensions acting as the invisible threads that bind everything together. As we explore the role of hidden dimensions in the nature of matter, we're not just uncovering new layers of the cosmos, we're redefining what it means to exist within it. The idea that matter might be shaped by forces beyond our perception is both humbling and exhilarating. It's a reminder that the universe's deepest secrets might not be hidden in the stars or the depths of atoms. They might be lurking in the unseen dimensions that shape everything we know. And as we continue to probe these mysteries, we're not just studying matter, we're stepping into a hidden world, one that could rewrite the story of existence itself. The universe is expanding, that much we know, but here's the twist: it's not just expanding, it's speeding up. This baffling phenomenon, discovered in the late 1990s, has left scientists scratching their heads. What could possibly be causing the cosmos to stretch faster and faster over time? Some theories point to an invisible force called dark energy, but what if the answer lies in something even more elusive: hidden dimensions? Picture the universe as a balloon being inflated. As it expands, the fabric of space stretches, carrying galaxies along with it. Now, imagine there's a hidden spring inside that balloon, pushing it outward with increasing force. This spring could represent the influence of extra dimensions, unseen layers of reality subtly driving the acceleration of the universe. Just as a hidden mechanism can power a clock, these dimensions might be the unseen engine behind the cosmos's rapid expansion. This idea isn't just a creative analogy, it's rooted in some of the most advanced theories in physics. For instance, certain models suggest that extra dimensions could create a kind of pressure, acting like a cosmic spring that pushes space outward. These dimensions wouldn't just exist as passive observers, they could actively shape the behavior of the universe, influencing the rate at which it expands. It's as if the universe is being pulled and stretched by forces we can't see, operating in realms beyond our perception. But how does this solve one of cosmology's greatest mysteries? The accelerating expansion of the universe poses a serious challenge to our understanding of gravity. According to Einstein's theory of general relativity, gravity should be slowing down the expansion, pulling galaxies and other structures closer together. Yet, observations show the opposite is happening. If hidden dimensions are at play, they could provide the missing piece of the puzzle. These unseen layers might counteract gravity's pull, acting as a cosmic counterbalance that drives the universe to expand faster and faster. This perspective doesn't just explain the acceleration, it also opens up thrilling possibilities for understanding the universe's ultimate fate. If hidden dimensions are influencing the expansion, they might hold the key to predicting whether the cosmos will continue to grow indefinitely, eventually slow down, or even collapse back on itself. It's a reminder that the universe's destiny might be shaped by forces we're only beginning to uncover. As we explore the mystery of the universe's expansion and its connection to hidden dimensions, we're not just solving a scientific puzzle, we're uncovering a deeper, more interconnected reality. The idea that the cosmos might be shaped by unseen layers is both humbling and exhilarating. It challenges us to rethink not just how the universe works, but what it truly is: a vast, multidimensional tapestry woven together by forces both seen and unseen. And as we continue to probe these mysteries, we're stepping into a hidden world, one that could redefine our understanding of existence itself. Imagine standing at the edge of an uncharted forest, knowing that somewhere within its depths lies a treasure beyond imagination. You can't see it yet, but every step you take brings you closer to uncovering something extraordinary. This is the essence of the hunt for hidden dimensions, a scientific treasure hunt where the prize isn't gold or jewels, but the keys to understanding the very fabric of reality. And just like any great expedition, the tools we use to explore this unknown territory are evolving faster than ever. The future of hidden dimensions research is a thrilling frontier, fueled by cutting-edge technologies and bold experiments. One of the most exciting developments is the rise of next-generation particle colliders, like the proposed Future Circular Collider. These massive machines will smash particles together at unprecedented energies, creating conditions that could reveal the faintest whispers of extra dimensions. Think of it as shining a brighter light into the forest, illuminating paths that were once shrouded in darkness. If hidden dimensions exist, these collisions might produce telltale signs: missing energy, unusual particle behavior, or even the fleeting appearance of particles that don't belong in our three-dimensional world. But particle colliders aren't the only tools in our arsenal. Gravitational wave detectors like LIGO and Virgo are opening new windows into the cosmos. These instruments listen to the ripples in space-time caused by cataclysmic events, like black hole mergers or neutron star collisions. If hidden dimensions are warping space-time in subtle ways, they could leave faint imprints in these gravitational waves, clues that could be decoded with increasingly sensitive technology. It's like hearing the faint echo of a distant drumbeat, hinting at the presence of something hidden just out of sight. And then there's the realm of astrophysics. Observations of the cosmic microwave background, the faint glow left over from the Big Bang, are becoming more precise than ever. Tiny anomalies in this ancient light could hold the fingerprints of higher dimensional physics, offering a glimpse into the universe's earliest moments. It's as if we're dusting off an ancient map, searching for faint markings that point the way to hidden treasures. What makes this hunt so exhilarating is the potential payoff. Discovering evidence of hidden dimensions wouldn't just solve a scientific mystery, it would revolutionize our understanding of the universe. It could explain why gravity is so weak, why dark matter and dark energy remain elusive, and even how the universe began. These extra dimensions might be the missing pieces of a cosmic puzzle, connecting the dots between the quantum world and the vastness of the cosmos. But the journey isn't just about the destination. As we push the boundaries of science, we're also redefining what's possible. Each experiment, each observation, brings us closer to a deeper, more interconnected reality. one where the boundaries between the seen and the unseen blur, revealing a universe far richer and more complex than we ever imagined. So, as we stand at the edge of this uncharted forest, let's take a moment to marvel at the journey ahead. The hunt for hidden dimensions isn't just a scientific quest, it's a testament to our curiosity, our ingenuity, and our unrelenting drive to uncover the mysteries of existence. And who knows, the treasure we find might just change everything. As we reach the end of this journey through the hidden dimensions of the universe, one thing is clear: the cosmos is far stranger and more intricate than we've ever imagined. From the mysterious pull of dark matter to the enigmatic depths of black holes, hidden dimensions offer a tantalizing framework to explain some of the universe's greatest puzzles. They challenge us to rethink not just what we know, but how we see reality itself, inviting us to consider that the world we perceive might be only a fraction of what truly exists. These theories don't just fill gaps in our understanding, they inspire us to dream bigger. What if the answers to questions about gravity, quantum mechanics, and the origins of the universe lie in dimensions we can't yet see? What if the fabric of reality is woven with threads we've only just begun to unravel? The pursuit of these ideas isn't just about solving scientific mysteries. It's about expanding the boundaries of human imagination and curiosity. But let's be honest, this isn't just a story for physicists or researchers. It's a story for anyone who's ever looked up at the night sky and wondered what's out there. Hidden dimensions remind us that the universe is full of surprises waiting for us to uncover them. They challenge us to keep asking questions, to keep exploring, and to stay open to the possibility that the answers might be stranger and more beautiful than we ever expected. So, what do you think? Could hidden dimensions hold the key to the universe's deepest secrets? Or are we just scratching the surface of an even grander mystery? Let's keep the conversation going. Drop your thoughts in the comments below, and let's explore these ideas together. And if you've enjoyed this journey into the unknown, don't forget to subscribe and join us for more mind-expanding explorations. Until next time, stay curious, stay inspired, and remember, the universe is full of wonders, both seen and unseen. Who knows what we'll discover when we dare to look beyond the visible? The adventure is just beginning.